All right, so today we're talking about the quantum mechanical model of the atom. We left off last lecture saying that the quantum mechanical model was our subject for today, and that's where we're going to pick up today. So the Heisenberg uncertainty principle is something you may have heard of from other classes or maybe from watching TV or out in the culture. It states that we can know the position but not the momentum of an electron, or we can know the momentum but not its position. In other words, an electron's not like a car, right? If you are watching cars drive down the road, you can see its position and you can tell its speed. You can measure speed, right? You can use a radar gun, whatever you want to use to measure speed. You can measure the speed of a car, you can measure position of a car at the same time, right? Car is a large macroscopic object. You running down the sidewalk, again, I can see your position, I can measure your speed, right? That's easy. When we're talking about an electron, electrons are very, 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 very small, right? And one of the things that we're not going to get into in this class, in Intro Chem, is the fact that an electron actually behaves both like a particle and like a wave. It's called a dual nature. We're not going to get into that in Intro Chem. We spend a lot of time talking about that in General Chem, but in Intro Chem, we don't get into that. And one of the things that tells us is that electrons are so small that their wave behavior greatly influences their wave properties greatly influence their behavior, which means that we can't treat an electron like we can treat a car or a baseball or a person, right? They're not large macroscopic objects. They are small, extremely small, and so their wave characteristics strongly influence their behavior. Therefore, we can know one but not the other. We can't know position and speed, so to say, just like you could for me, right? Me running down the sidewalk, that's easy. And so the Heisenberg uncertainty principle is kind of summarized with a propeller, right? When you turn the propeller on, or your ceiling fan, when you're laying in bed tonight, you can get your ceiling fan and think about chemistry, right? When you turn the propeller on, you know that the blade is somewhere in this vicinity, right? But do you know its exact position? No. And if you're smart, you know where you can put your hand and where you can't, right? If this is obviously not up in the air, let's pretend that this is in the shop. You're working on it, and you're trying to make sure the propeller works before you take off, right? You can say, okay, I can put my hand right here, no problem. But if I put my hand right here, bad news, right? Because if I point to a propeller blade and say, yep, there's the blade, it's already moved, right? I can't know position and its speed at the same time. But I know a general area where it's located. And I can say with pretty high confidence, my hand is safe here, my hand is not safe here. Right? And so how does that translate into the quantum model? So because we don't know exact locations, but we have areas where we think it's most likely that we will find them, the quantum model tells us the area where it is most probable that we will find our electron. Okay, it's the probability of finding an electron in a given space. We define that area as an orbital. Bohr used that word too, right? We talked about energy levels in the Bohr model. Well, we're going to reuse that same word, but we're going to give it a different meaning. Orbital is an area where it is highly likely to find our electron. So does it matter that we can't know exact locations? No, it's not going to cause us to lose any sleep. Just like with my propeller example, right? You're not going to have any problems knowing, yes, I can put my hand here. No, I can't put my hand right here. But I know the area where it is most likely that my arm will get lopped off if I stick it. Right? That's the most important thing if you're working on this propeller blade or your bird flying through the air. So an orbital gives us the area where it is most likely that you'll find an electron. And that's what we look at in the quantum model. Okay, remember the Bohr model, the planetary model, it has these nice circular orbits. Everything's nice and pretty and neat, and that's not how it works, right? We can't know exact locations of electrons. The particulate nature versus the wave nature, they behave like waves and like particles, whereas you just behave like a particle. So we have to use a whole new branch of physics called quantum mechanics to explain the behavior of electrons. Okay, and so electron position is only probable, right? We're saying it's most probable to find an electron here. Does this make sense? You're not going to know its exact position. Don't let that bother you. It doesn't bother me. If it doesn't bother me, it shouldn't bother you. Okay, so quantum mechanics is a mathematically based model. It's a math-based model. It's based on the wave function. What's the wave function? It's a set of three-dimensional coordinates. Right? So if you think about your algebra class you took in high school, or maybe you're taking college algebra now, right? That's x, y. That's two-dimensional math, right? So three-dimensional math would include the z component as well. And so the wave function is a set of coordinates that give the area where it is most probable that you'll find your electron. Okay, so if you want to think about a three-dimensional graph, just think about the corner of a room. Right, so if I stand right here in this nice block tile, I can measure my distance from this wall. I can measure my distance from this wall, and I can measure my distance from the corner, right? That's x, y, and z. Okay, so if you want to think of three dimensions as just like the corner of a room, that's an easy way to put it. And then that tile has distances from all three axes. Now the bad news is you can't handle the truth. Sorry, hate to be the one to inform you of this, but the good news is that concepts are all you're going to need to know, okay? You're not going to have to do any nasty calculus in this class. So, like I just said, we know propellers are somewhere. We're not going to lose any sleep over, you know, I don't know exactly where it is. It's impossible for me to know. It's okay. Orbitals represent the area where it's most likely you'll find an electron. Keep saying that because it's important that you know what that is, right? All of the quantum mechanical model is based on this idea that we have to have a general idea of where the electron is. We're not going to know its exact position. Because you can define your exact position, or that chair's exact position, or my box of tissue's exact position, but you can't do that for an electron. Okay? So make sure you understand that quantum mechanics is a branch of physics that we have to use to describe things at the molecular, at the atomic level. Right? We can't use your physics that you use to describe me running down the hall. That's classical physics. Quantum mechanics is at a very, very, very small level. So we're going to be drawing some fun shapes today. We're going to be goofy. You're going to feel goofy doing it. Maybe you did this in high school. Maybe you didn't. But these goofy shapes represent areas where it's most likely that you'll find your electron. That's why we're drawing these goofy shapes. Okay? We're not just making you memorize it for the sake of memorizing it. These goofy shapes that you're going to learn how to draw today represent area where it's most likely to find an electron. All right, so we're going to talk about quantum numbers. An orbital is defined by a set of 4 quantum numbers. So an orbital is defined by 4 quantum numbers. And in Intro Chem, you are responsible for explaining and defining 2 of those. In Gen Chem, we'll go into all 4, but Intro Chem students only need to know 2 quantum numbers. Gen Chem students got to go 4. Right? One of the main differences between Intro Chem and Gen Chem is the depth that we go into the material, the speed that we go through the material. And so here's an example of a difference between Intro Chem and Gen Chem. So for those of you online, if you're watching this as a Gen Chem student, sorry, bud, you got to know all 4. If you're an online student watching this as an Intro Chem, yay, you only get to know 2. Okay, so it's defined by 4 quantum numbers. In Intro Chem, you'll need to know 2. In Gen Chem, you'll need to know all 4. But the thing is, these numbers aren't difficult, okay? The first one is called the principal quantum number. Principal quantum number, we represent it with a lowercase n. And this tells us the size of the orbital, the size. So the principal quantum number, which we represent with a lowercase n, tells us the size. What's the size of the orbital? N can be any number greater than or equal to 1. And it must be a whole number. Okay? You can't have n of 1.5 or 2.6. It has to be a whole number greater than or equal to 1. N cannot be 0. Cannot be 0. Let's talk about why. If I say to you, okay, everybody draw a circle with a radius of 0. Could you do that? If the radius is 0, then there's no circle, right? The same thing's true here. N is telling you the size. Now, I know this is kind of skewed for us ladies because there is a size 0, right? But just pretend that that doesn't exist. If I say, okay, you stand on the scale and your mass is 0, then you're not standing on the scale because you don't exist, right? You cannot have a circle with a radius of 0. You cannot have a mass of 0 and still exist. Okay, so the quantum number n, because it's telling us size, absolutely cannot be 0. It can be 1 or greater, and again, it must be a whole number, right? Not 1.3, not 2.6, got to be a whole number. And as we increase n, we're increasing the size, right? The larger the value of n, the larger the orbital. Makes sense? If I said draw a circle with a radius of 1 centimeter, draw a circle with a radius of 2 centimeters, the radius of 2 is going to be a lot bigger of a circle than the radius of 1. Right? So n tells us the size. Now the other quantum number that you need to know in Intro Chem is called angular momentum, which we represent with a lowercase l. Lowercase l. I write it in cursive so that you don't think I'm drawing the number 1. You need more tissues. I've got more tissues. Okay, I always put that in cursive just so that you don't think I'm drawing the number 1. That's why I put it in cursive. It's a lowercase l. Okay, I write in cursive to distinguish it from the number 1. This tells us the shape of the orbital. L tells us the shape. And there's a little bit of memorization that's going to be involved with this. So you're just going to have to bear with me. But once you get that part memorized, I think it won't be difficult. I don't think it's going to be difficult, period. But you are going to have to do some memorizing. Just telling you now. And I am going to give myself a blank slide, so I've got room to write. We're going to make ourselves a chart. Okay. Value of L. Okay. And then we're also going to put name of shape. And we're going to do a sketch of shape. Okay, before we get started though, L, make a note to yourself. L can equal 0, okay? L can be any whole number up to n minus 1. Okay, so for instance, if n equals 3, then L could be 0, 1, or 2, right? Zero, 1, or 2. In other words, L cannot equal N, right? So those are the restrictions on L, right? We learned our restriction on N. N cannot be 0. That's the only restriction you need to worry about for N. L has different restriction. L is allowed to be 0, but L cannot equal N. Okay, L can be any number up to n minus 1. So if n equals 3, then L could be 0, 1, or 2. It couldn't be 3. If n equals 3 and L equals 3, and I said, what's orbital is drawn here, you would say undefined, doesn't exist. Okay? So let's go through this chart. The value of L is 0, then the name of that shape is called an s orbital. Remember, these shapes are called orbitals. So that's called an s orbital. And an s orbital just looks like a sphere. All right, the bigger the value of n, the bigger that circle would be. Makes sense? That one's easy to remember because it looks like its value of L. If L equals 1, then you've got a p orbital. P orbital. Now, when we get into general chem, we'll learn about how you can orient those orbitals, oriented along the x versus oriented along the y versus oriented along the z. But in this class, we're not worrying about orientation. Okay, you can draw your p orbital any orientation you want. So you can draw a p orbital The p orbital looks like a figure 8, or if you draw it on its side, it looks like an infinity, right? Or you can draw it kind of diagonal. It's got that figure 8 kind of shape. All three of those would be accepted. If I said, draw me a p orbital, and you drew one of those three, I'm happy, okay? Because we only care about the shape, we don't care about the orientation. In Gen Chem, we'll worry about orientation. If L equals 2, you have a d orbital. And again, in Gen Chem, we'll get obsessive about orientation. Intro Chem, we don't. You could draw a d orbital like a clover. Okay, that's acceptable. There's also a version of a d orbital that looks like a figure 8 with a hula hoop. I'd accept either one, because again, we don't care about orientation in Intro Chem. Gen Chem we do, Intro Chem we don't. And then if L equals 3, you have an f orbital. And these guys are nasty. Okay? Nasty to draw. I'm not going to make you draw an f orbital. So maybe you should draw that as a happy face. I don't know. You're not going to have to draw it. Okay? I'm not going to make you draw an f orbital. I struggle to draw an f orbital. If I can't draw, I'm not going to ask you to draw. So you don't have to draw an f orbital. You would just need to know its name and the value of L that goes along with it. Okay? If L equals 3, then you have an f orbital, but I won't ask you to draw it. Are we good on the angular momentum quantum number? All right. So you definitely want to put in your notes that that's something you need to commit to memory. All right, so if L equals 0, s orbital, L equals 1, p orbital, L equals 2, d orbital, L equals 3, f orbital. All right, so there would be an s orbital. There would be p orbitals. Again, look, these are the different orientations. Intro Chem, we don't care about orientation. This one's oriented along the z, that one's oriented along the x, that one's oriented along the y. And Intro Chem, I don't care how you orient it, as long as you get the shape right. There are 4 of the d orbitals. The 4th one and the 5th one looks like a p orbital with a hula hoop. And then, like I said, f orbitals are not pretty to draw, so I'm not going to make you draw them. Okay. Now, the 2 other quantum numbers which you're not responsible for in this class, m sub L is orientation. I've already mentioned it. And m sub s is telling you which direction it's spinning. You're not responsible for these 2 in Intro Chem, so this is just for your general knowledge. Go on and take Gen Chem, and we'll get into the nuts and bolts of those. Okay, so what do I need to know for the test as an Intro Chem student? You need to be able to explain N and L, definitely. Describe it in words. What is N? N defines the size of the orbital. You have to be able to define that word, right? Explain what L is. L tells the shape of the orbital, right? Is it a circle? Is it a figure 8? Is it a clover? What? Also, if I give you the name of an orbital, you tell me the value of N, and you tell me the value of L. Or vice versa. If I give you a value of L, and I give you a value of N, and I say draw it, right? You need to be able to do that too. So these are the kinds of things that I'm going to ask you to do in this class. I'm going to give you some practice problems to do. We're going to do some here in lecture, and then we're going to do enrichment on this kind of stuff tomorrow as well. So I'm going to pause the recording for people jotting this kind of stuff down. Okay. Here are some problems that I want you to try. So those of you watching it online, state the values of N and L for the following orbitals. So the name is 3D. You tell me what N is. You tell me what L is. The name is 2P. You tell me N. You tell me L. The name is 6F. You tell me N. You tell me L. And the name is 1S. You tell me N, and you tell me L. Pause the recording. All right, let's go over these. State the values of N and L for the following orbitals. So this is something I see students write on the corner of their test. As soon as I hand them their test, they start writing this on the top corner, right? 0, 1, 2, 3, S, P, E, F, right? Because that's kind of a condensed version of that table that we just drew a second ago. So if we have a 3D orbital, that means N equals, that's the value in front, right? So N is right here, and L is right here. And now you need to translate that into a number. So what is the value of N for 3D? 3, right? And what's the value of L? Well, D corresponds to 2. So that's how you do that problem. Did you get it right? Okay. What's the value of N here? N equals 2. And what's the value of L for a p orbital? 1. Okay. Notice we're following our rule, because what's the restriction on L? L can be any number up to n minus 1, right? N equals 6. And what's the value of L for an f orbital? 3. And n equals 1. Uh-oh. What happens here? Is it okay to have L be 0? Yes. A lot of students forget this. They get the N and L rule backwards. If I say things like, does a 1s orbital exist? They'll say stuff like, no, L can't be 0. And they're using the wrong rule, right? A lot of students will fall into this trap. I'll ask stuff like this all the time. Does a 1s orbital exist? The answer would be yes, of course, because N equals 1 and L equals 0, right? L can be 0. But what if I said something like, does a 0p orbital exist? The answer would be no, right? Because N can't be 0. So just be prepared for those kinds of little variations. I like to throw at you to see if you're keeping your rules straight. Okay. Here's some more problems that I'd like you to try. I gotta pull it all the way down, I guess. I'll pause the video and give you a chance to try these. Sketch the following orbitals. 3p, 2s, 4d, 1s. All right, let's go over the answers here. Sketching these orbitals. Now, when we're drawing orbitals, we need to have a way to distinguish scale. So what I recommend doing is drawing it on an axis, drawing it on a grid, and then using tick marks to denote size. So 3p, what shape is a p orbital? I don't care how you orient it, right? So you could draw it this way or that way or diagonally, right? How do I show that N equals 3? 1, 2, 3, 1, 2, 3. Makes sense? If you drew yours going up and down, you'd go 3 up, 3 down. If you drew yours diagonally, you'd go 3 in each direction. Because if you just drew this, I'd say, great, you know the shape, but you need to be able to tell me that you know the size too. Because if you drew that and the person next to you draws that, scale is relative there, right? We need to have a way of making it so that I know everybody knows that the size equals 3. Makes sense? All right, s orbitals have what shape? They look like a simple sphere, right? And so to quantify that size, just count out 2. Do your best. Right. N equals 2. For 4D, it's considerably bigger. Now a d orbital can look a lot of different ways, right? You could draw mine's a little asymmetric there. right? You could have also drawn your d orbital in between, right? Because there are 5 orientations of a d orbital. As long as the scale is correct, right? You could have also drawn a d orbital. You could have drawn your d orbital in between axes through different axes, right? As long as you show me either the cloverleaf shape in any configuration, really, or the p orbital with the hula hoop, I accept either one. Okay? And then what's the difference going to be between 1s and 2s? Right, it's just going to be the scale, the size. So if you wanted to even draw those on the same axes, you could, right? There would be 1s in the middle. If I said, between these two, which one's got a greater probability of finding an electron? You've got a higher probability of finding an electron in 1s or 2s? In the 2s, right? Think about it like playing darts. Which dartboard are you more likely to hit? The bigger one or the smaller one? Right? You've got a greater probability if we're comparing 1s versus 2s. Who's got the bigger probability of containing an electron? The bigger area, right? Bigger search area. We good on these? Okay. Got some more for you to do. All right, for the following values of n and L, determine the name of the orbital and then sketch it. So I will pause the video, give you a few minutes to try this. All right, let's go over this one. So I've given you values of n and L and asked you to give me the name of the orbital and then sketch the orbital. All right, so let's make our little cheat sheet. 0, 1, 2, 3, S, P, D, F. Okay, n equals 2 and L equals 1. So that would be what? What name? 2P. First of all, does that fall into the rules? Yes, because remember, what are the rules? N cannot equal 0, and what else? L must be less than n, right? Because L can be any number up to n minus 1. That does fall into that rule, so we're good. So 2p, that does exist. How would we draw a 2p orbital? 1, 2, 1, 2. Right? I just decided to go up and down that time. Okay, what about this one? N equals 3 and L equals 4. Right, that doesn't exist. Why? Exactly. Does not exist because why? L is greater than N. L is greater than N, which is not allowed. Right? If you were to name it, what would the name of that be? 3F, right? Oh, yeah, L equals 4. We don't have L equals 4 on our board, do we? Just kidding. All right, N equals 1 and L equals 1. If we were to name it, what would its name be? 1P. Does that exist? Why not? Right, this also does not exist. Good. These are the kind of little traps I like to lay to see who falls into them. All right, let's go to the next ones. N equals 4 and L equals 2. Oh, erased my sheet. 0, 1, 2, 3, S, P, D, F. Okay. So n equals 4 and L equals 2. Is that an allowed combination? Yes. Yes. What's the name of that? 4D. Right. So D orbital. My grid big enough. Boy, my scale stinks. That's okay. Right. Or you could have drawn it. Don't forget the hula hoop though. Or you could have drawn the whole thing rotated 90 degrees, or you could have drawn it flat. Right? There are a lot of orientations that I would accept. N equals 2 and L equals 0. Is that an allowed combination? Yes. What's the name of that? 2S, which we drew a minute ago. How do we feel on this kind of problem, where I give you values of N and L and then you give me the name? Yes? All right. Let's go to another kind of problem. And then when we go over after we go over this one, we'll take a mental break. Do the following orbitals exist? Why or why not? So take a minute and try these. This will be the last set we do, and then we'll take a mental break. I'll pause the video. Let's go through this problem and see what we came up with. Do the following exist? Why or why not? You want to make your cheat sheet? 0, 1, 2, 3, S, P, D, F. Okay, 2D. For the 2D orbital to exist, that would mean that N equals 2 and L equals what? 2. Is that combination allowed? No. Forbidden. Right? N cannot equal L. For 4P to exist, that would mean N equals 4 and L equals what? 1. Is that an allowed combination? Yes. This exists. For 1P, that would mean what? N equals 1 and L equals 1. So what does that mean? That does not exist, right? Forbidden, does not exist, no solution, whatever you want to put there, right? And then 2S, we've drawn about 5 times now. So yes, it does exist, right? Let's prove why. N equals 2. L equals 0. Yes, that exists. The one that students mess up the most involves the zeros, right? They'll say that N, and they'll say S can't equal 0, therefore that doesn't mean. They'll say that L can't be 0, and that's wrong, right? L can be 0, N cannot. All right, I'm going to pause the recording for a few minutes. Let's take a mental break since we've been at it for an hour now. All right, now that we are all mentally refreshed, let's kick back up. So next week in lab, we're going to be doing flame tests. Maybe you did this in high school or prior classes. So what we'll be doing is we're going to take a sample, and then we're going to put it in the Bunsen burner. We're going to see these pretty colors. And remember last week when we were talking about the Bohr model, I said, well, there are some things about the Bohr model that actually are correct. And one of the things that the Bohr model does get correct is that when we add energy to an electron, it does jump up to a different orbital. That's true. That is a true statement. And then when that electron falls back down to the ground state, it releases energy in the form of light that we can see. And so each substance is going to have a unique chemical signature in a flame test. And that's what we're going to be doing, not this week in lab, but next week. And I know one of the things that I ask you in the post-lab questions is to explain this observation from a atomic theory explanation. So that's what I'm going to be looking for in that question. Yeah, that's next week. So flame test next week. It's fun. It's one of my favorites. Lots of pretty colors. Okay. Let's talk about what the Pauli exclusion principle tells us. it tells us that no two electrons in an atom can have the same 4 quantum numbers. So why could no single pair of electrons have the same quantum numbers? Well, if we think of quantum numbers as like directions to get to your electron, or where it's most likely to find your electron, for you to have the same coordinates as the person next to you, that means that, you know, the other person's sitting in your lap, right? If we said, okay, let's think of coordinates for how to get to where you are right now, as specific as possible, we would first say the state. Well, I guess we even get more broad than that. We'd say that you're in the United States, and then we'd say the state that you're in, and then we'd say what county we're in, and then we'd say what campus you're on, and then we'd say what building you're in, what room number, what tile number from the door, right? We could get really, really specific about that. And obviously, you and the person next to you would have a whole lot in common, but that very last number would be different, right? Because you're in seat number 1, person next to you is in seat number 2, right? So no two electrons can have the same 4 quantum numbers. Every electron needs to have its own unique set. Okay, that's what Pauli exclusion principle tells us. So for hydrogen, who cares? Hydrogen's got 1 electron, no big deal. What if we're talking about manganese? It's got 25 electrons, right? We're going to have to write directions to get to all 25 electrons. Does everyone understand what the Pauli exclusion principle tells us? Okay, so we're going to write electron configurations. What is an electron configuration? Okay, an electron configuration is basically just a list of the locations of all the electrons in your atom, or at least the general locations, right? If we're talking about manganese, it's 25. Some electrons are here, some electrons are here, some here, 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 right? So the rules for writing electron configurations are pretty easy. We're going to use the periodic table, and by the way, if you have the one that I gave you last week, that cardstock one, you might want to take it out. Use your periodic table to figure out how many electrons are in the atom. The number of electrons, is that the same as the mass number or the atomic number? Atomic number, right? Because remember, in a neutral atom, the number of protons and the number of electrons equal each other. So you've got to know how many electrons you're dealing with. So the first thing you do is you take out your periodic table. And then you need to write your electron configuration, making sure that all the electrons are represented. So if we're doing manganese, manganese has 25 electrons. I need to check my work by making sure that all 25 electrons are in that electron configuration. And that's really it. And then there's a random bullet point. Okay, so there are 2 methods for writing electron configurations. I personally have no preference which you go with, okay? Whichever one makes you happy. So the first one is called the diagonal rule. Maybe you've seen this before, maybe you haven't. So if you do go with this method, you'll need to learn how to draw it, okay? It's not difficult to draw. I'm going to go over how to draw it right now. And this will be nice for you if you're writing on paper with lines. So make a row, make a column, 1 through 8. Okay, 1 through 8. Now pinch 1 off the top and 1 off the bottom. Give yourself a little bit of room and go 2 through 7. Right beside, so staying in the same row. Okay. Now pinch 1 off the top and 1 off the bottom again. Do 3 through 6. And then pinch 1 off the top and 1 off the bottom again, and your last column will only be 4 and 5. Okay? See, looks like a diagonal. All right, now let's fill it in. The first column is all S's. The second column is all P's. Third column is all D's. And fourth column is all F's. And now we need a little superscript to go with it. So the first column all has the superscript of 2. Second column is 6. Third column is 10. Last column is 14. Now this superscript is the maximum number of electrons you could put in that orbital. Okay, so a 1s orbital can hold a maximum of 2. But you could put 1 in there if you wanted to. A 2p orbital can hold a maximum of 6, but you could put 3 in there if you wanted to. Okay, this number is the max number. So in a 4f, you can have 4f3. You can have 3 in that f orbital. You don't have to fill it all the way up. Now to read it, you start right here. And then you read down, and then over, and then you just start going diagonally. So here, then you loop back around and go here, then you loop back around and go here, and you loop back around and go here, loop back around and go here, loop back around and go here. Now just FYI, 8s does not exist. And there's no such thing. We put it here so it's nice and symmetric. Okay, so it makes a nice pretty triangle. But just so you know, there is no such thing as an 8s. That's just there kind of as a placeholder, because otherwise you just have a hole. And I don't like having a hole, so I plop that in there. Okay, but that doesn't really exist. There's no such thing. So let's do some examples. Let's look at periodic table. Let's do nitrogen. So first thing you need to do is look up how many electrons nitrogen has. How many is it? 7, right? So here we go. You start at the top. 1s2. Okay, we want all my little superscripts to add up to 7. So now I got to go down. 2s2. So 2 plus 2 is 4. So then what's next? 2p what? Do I need to put all 6 in there? Just 3, right. Do you see how to do that? You just start here at the top and then you keep going until your superscripts add up to the number of electrons in your atom. So why don't you try, I'll give you a second to try. Let's do a couple. Let's do sulfur. And let's do titanium. Actually, I'm not going to make you go into a D block yet. That's kind of mean. We're just getting started. Let's do sulfur and sodium. A little bit shorter. I'll pause the video. All right, let's go over these. So sulfur has how many electrons? 16. So let's see. 1s2, 2s2, 2p6. That gets me 10. 3s2. Then what do I do? Loop back around. 3p what? 2, right? Sulfur has 16. It's not 3p2, it'd be 3p4. Right? Because that's 10, that's 6, 16. All right, now let's do sodium. Sodium's got 11 electrons. So 1s2, 2s2, 2p6, that gets me to 10. So now it's just 3s what? 1. Do we agree on how to do this using the diagonal rule? So everybody cool on how to do the diagonal rule. So if this works for you, awesome, use it. Okay, just remember how to draw. It's not my personal choice, but who cares? I'm not the one taking the test, right? If this works for you, then by all means, use it. The second method I'm going to teach you will give you the exact same answer. You get the exact same answer. And like I said, I don't really care if you use this method or if you use the next method. It makes no difference to me. So the second method is the periodic table. If you've got some highlighters or different colors of markers, you can pull those out. They might be helpful. But if you don't have them, that's fine too. So here's our periodic table. All right, that's the periodic table that I gave you. This is the exact same version of the periodic table you'll get on a test. So if I give you a test or a quiz, this will be included, always. I'll always give you this version of the periodic table. So you would just need to remember where to draw these things on your periodic table. Okay, so the first thing you want to do, now we're imagining that helium is sitting right here next to hydrogen. Okay, so just imagine helium sitting here next to hydrogen. So draw a rectangle around these two and call it the S block. S block. So again, we're imagining helium sitting right here. First two groups of the periodic table, they are called the S block. All right, next, you want to go boron down to neodymium, I think. It's one of the new ones. All the way over to the end and back up to neon. Okay, these guys are the P block. Those are the P block. Now everything in between, those guys are called the transition metals. They're also called the D block. So everything in between the S block and the P block is called the D block. And then what's left is the F block. Okay, so just label these sections on your periodic table. All right, here's what I'm going to do. Have this just kind of handy so I don't have to sketch it. Took a screenshot there, cropping off all the excess stuff. Make it a size that we can read. All right, that works. Well, let's move it down just a touch. I'm not that tall. There we go. So let's do an example using the periodic table. That actually works pretty well. All right, so let's do some examples. Let's do sulfur. We already did sulfur. Let's prove to ourselves why you get the same answer. Sulfur's still got 16 electrons. Now, how you do it using the periodic table is you just start, you look at where you want to go, right? So this is our destination, okay? And you just start at the beginning, and then you count off. So this is row, the row number is the value of n, okay? So I just, notice this is why I said there's no such thing as 8s. There's no period 8 of the periodic table. So this is all the value of n. This is n equals 1, 2, 3, 4, 5, 6, 7. No such thing as n equals 8, because there's no 8th row of the periodic table, if you notice. So we're in row 1. Well, it should be correct. We're in period 1. Period 1, that means the value of n is 1. We're in the S block, element 1. So that's 1s1, 1s2. All right, so there's 1s2. But am I to my destination yet? No, I got to keep going until I get to my destination. So now I go into the n equals 2 row. 2s1, 2s2. gives me 2s2. But I'm not to my destination yet. I'm still in n equals 2, so I just keep going. 2p, 1, 2, 3, 4, 5, 6. So that gets me up to 2p6. Am I to my destination yet, though? Nope, got to go to n equals 3. 3s1, 3s2. 3s2. Still not to my destination, got to keep going. Period 3. So 3p, 1, 2, 3, 4. Include your destination as part of your counting, okay? And that's the same answer we got a minute ago when we did it using the diagonal rule. I prefer this method, that's just me personally. I really don't care which method you use, diagonal rule versus periodic table. Makes no difference to me. So just to make sure we're good at this, why don't you try? I'll just give you one to try. I think you can handle titanium now. I gave it to you a minute ago and I said, we don't want to do that yet. All right, let's see what we got. So we're doing titanium. Now there is one little glitch in this system that I didn't tell you about yet, and I intentionally didn't tell you about it yet because I want to see if anyone caught it. So let's see if you caught it. Maybe you did, maybe you didn't. Depends on how well you memorize the diagonal rule. All right, so we're starting at titanium. I mean, we're doing titanium. We're starting here. So this is, you're going to feel really redundant, right? 1s2, because there's s1, there's s2. Now we're going to n equals 2. 2s1, 2s2. We're still equal, n equals 2. 2p, 1, 2, 3, 4, 5, 6. All right, we got to go to n equals 3 because we're going to right here. So 3s1, 3s2. N equals 3. 1, 2, 3, 4, 5, 6. 3p6. All right, 4s1, 4s2. Now here's what happens. When you hit the D block, decrease n by 1 in the D block. The value of n decreases by 1 in the D block. If you wrote 4D next, that's incorrect. And I didn't tell you this on purpose. I just wanted to see if anyone would notice this glitch. Because if you look at the diagonal rule, well, that's a mess because I'm writing on the screen. If you look at the diagonal rule, it goes 4s, 3D, right? It goes from 4 to 3, and then it goes 5 to 4, and then it goes 7 to, excuse me, 5 to 4, 6 to, well, that's going into F block. That's why it does that. Okay, we're not going to deal with F block in this class. But notice 5 to 4, 4 to 3, okay? And the reason for this is a nasty quantum mechanical answer that you don't need to be able to explain in this class. Just know that when you hit the D block, the value of n decreases by 1. Okay, so the next number is not 4D, it's 3D. And it's 3D what? 3D2. Okay, don't forget to include the destination as one of the numbers you're counting. Okay, because a lot of students will omit it. They'll say, well, I'm there. Well, no, you're not there. You're one in front of it. Right? You got to get one to it. So just make a note to yourself. In the D block, we decrease the value of n by 1. Now these F block elements, we're imagining them right here. So if I were to ask you to do, say, tungsten, right, you would go 6s2, then you go down and deal with these. I'm not going to make you do anything that deals with the F block in Intro Chem, so don't stress out about that. Okay. Questions on how we use the periodic table. Like I said, this is my personal preference. However, whatever method you prefer, that's entirely up to you. Now let's talk about something that I think you might have picked up on by now. And that is, when you do these, let's pretend that we do krypton or xenon or zinc or any of these, they're all going to have a whole lot in common, right? You're going to start writing this so many times, you're going to have this memorized. You've got a lot of stuff in common. 1s2, 2s2, all the way up to 3s2 in common there, all the way up to 3s2 in common here, right? So we can actually use a shortcut. Hey, who doesn't like shortcuts? And it's called the noble gas shortcut. All right, so this group right here, these are called the noble gases. And these guys all have a completely filled outer shell. In other words, if you were doing helium, it's just 1s2. If you were doing neon, it's 1s2, 2p6, right? 3s2, 3p6. It fills it all the way up, right? So we can use them as a shortcut to fill in the redundant stuff. So if we were doing sulfur using the shortcut, we would, that was for titanium. For doing sulfur using the shortcut, what you do is you find your element, and then you go up a row and to the end. So your noble gas that you're going to use for the shortcut is neon. And neon, what is neon's electron configuration? It's 1s2, 2s2, 2p6, right? So that is the exact electron configuration for neon. So neon takes the place of all this, and now all you have to do are the leftovers in your row. 2p6, excuse me, 1s2, 2s2, 2p6, get you right here. So neon takes care of this, and all you have to do are the leftovers in your particular row. So 3s2, and then 3p, 1, 2, 3, 4. Pretty neat, huh? Yes? So if we were going to do titanium using the shortcut, titanium's right here. So what element goes in the brackets for titanium? Argon, right. Argon gets us all the way up to 3p6. Right, so you put argon in brackets. And now all your leftovers are 4s2 and then 3d2. Makes sense? Makes sense? Now, if you're doing the diagonal rule, here's my warning about the diagonal rule. If you're doing the diagonal rule, you need to figure out where your noble gas ends so that you can start at the right place. Okay, because I've seen students do this. If they're doing sulfur, they'll say neon, and then they'll start at the beginning, and that doesn't make sense, right? Neon ends at, right? I have to start here now. Okay, so if you're using the noble gas shortcut on the diagonal rule, figure out where yours ends off so that you know where to start. Okay, because otherwise you'd be starting at the beginning. That's hydrogen. That's defeating the point of the shortcut, right? Because you're still going to end up doing what you are trying to avoid. So just keep that in mind. Okay. Personally, I prefer the periodic table. That's just me. You pick the one that works for you. So why don't we do, just for practice, write me some shortcuts using either the periodic table or the diagonal rule. Give me shortcut for, let's do bromine, and let's do yttrium. Pause the video. Zoom. So I prefer periodic table. I think it's way faster. But again, if you want to use the diagonal rule, just remember, figure out where your element noble gas stops so that you can start in the right place. Oops, wrong direction. Okay, so for bromine, bromine's number 35. So what goes in brackets? Argon. And then you're responsible for the leftovers. So that would be 4s2, then what? 3d10, then what? 4p5. Good. Any questions on shortcut for bromine? All right, yttrium's down here. It's number 39. What goes in brackets here? Krypton, right? And then we deal with the leftovers. So that's 5s2, then what? 4d1. Right. How do we feel about noble gas shortcuts? Easy and peasy, right? All right. So on the exam, you will get a blank periodic table. It'll be completely blank. And you'll also get it on quizzes too. You just need to remember where the SPD, I mean, you can commit the F block to memory, but I'm not going to make you do anything that goes through the F block in this class. All right, let's talk about orbital diagrams. Orbital diagrams. So orbital diagrams are just another way to represent an electron configuration. They're just the exact same information represented again. Okay, and you're going to use half arrows to represent electrons, one pointing up, one pointing down, right? Because in a given orbital, if you have two electrons, one's orbiting clockwise, or one's rotating clockwise, one's rotating counterclockwise. So that's why you've got one up and one down. And I just realized there's a figure that I want to put in the slide here that for some reason isn't. So I'm going to pause the recording for a second. Well, I can't find the file that I was looking for, so I'm just going to have to draw it. All right, orbital diagrams just represent orbitals. Okay, it's another way of representing an electron configuration. On a test, I have a file somewhere. I'm not sure where it is at the moment. It's lost. I have a file that saves me from having to draw this every time. I will give you the boxes. You just need to fill them in. Okay, I'll give you the boxes, and I'll usually give you way more than you need so that you know when to stop. Okay, so I will give you these boxes, and then your job is to fill it in. Like I said, I had a file somewhere. I'm just empty. Can't locate it at the moment. I'm sure I'll find it as soon as class is over. Now, how do you fill it up? These, well, it's half arrows. And this are electrons. Okay? That's how we represent an electron. So I will give you this. You just need to fill it in. All right. Oh, forgot to talk about Hund's rule. Yeah. So Hund's rule says, we're just going to put it in layman's terms. Give every electron its own box until forced to pair up. All right, so for instance, if I rent a big van and we're all going on a field trip, all right, first person gets in, sprawls out, takes up a whole seat, right? Second person gets in, sprawls out, takes a whole seat. Third person, fourth person, everybody's got their own seats. Now person number 5 gets in. Well, now, move over, we gotta share, right? Person number 6 gets in, now we gotta share, right? Hund's rule says that we want to split up electrons at the same energy level until we absolutely have to share. So let's do an example. I will give you this. Now you would fill it in for, let's do fluorine. So fluorine's got 9 electrons, right? So we start here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? We fill them in, and so we force them not to share. And notice that matches the electron configuration. 1s2, 2s2, 2p5. 2, 2, 5. See how that works? It's nice and symmetric. So why don't you try real quick filling it in for why don't you do it for silicon? You fill it in for silicon real quick. I'll pause the video. All right, let's see what you came up with. We're doing silicon, 14 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Do you have the last two in their separate boxes? If you have these two together in the same box, put -1/2 on your page. Okay? Because you want to give every electron its own box until you are forcing them to pair up. So if you drew this, I would say -1/2. Okay? Because you want to give every electron its own box to obey Hund's rule. Because we're maximizing repulsions, in other words. We're getting these electrons furthest away from each other. Okay? And then this matches the electron configuration. 1s2, 2s2, 2p6, 3s2, 3p2. Right? That matches the electron configuration. All right, there's one last thing we need to talk about in the last 10 minutes or 5 minutes here. We can make it work. And these are anomalies in the D block. So on your periodic table, you need to put a little star in these boxes. Chromium, molybdenum, copper, and silver. Put little stars in those boxes because these behave in a way that you would not expect. They do something that you wouldn't expect them to do. And so let's talk about what that anomaly is. So if we're doing, actually let me have my periodic table back. That was convenient having it right there. If we're doing, the same rule applies to chromium as molybdenum, and the same rule applies to copper and silver. Now technically it applies to tungsten and sborgium, but those two require you to go through the F block, which I'm not going to make you do. Okay? And this rule also applies to progintium and gold, but again, I'm not going to make you go through the F block. So if we're doing the electron configuration for chromium, we would expect this. We'd expect my robe. 4s2, 3d4, right? That's what you'd expect. Yes? Oh, well, forgot my noble gas configuration. It would be argon. 4s2, 3d4, right? That's what you'd expect. The orbital diagram for that would look like this. 4s, 3d, right? What you actually observe is this, argon 4s1, 3d5. That's the actual correct electron configuration. What happens here? One of these electrons from the S block gets taken by the D block. What's the reason? From a quantum mechanical standpoint, more stable to have D block fully half filled. Okay? And it only happens if you're one away. If you're one away. Okay, it only affects chromium. It would not affect vanadium, right? Vanadium's 2 away, and 2 electrons is just too many to steal. Okay, it's just 1. And then it will be the same thing in molybdenum. The only difference is it'd be 5s and 4d instead of 4s and 3d. So what do you think the case is going to be with copper? Here's Cu. Copper's got 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? That's what you'd expect. Looks like that. What do we observe? 4s1, 3d, 10. Again, that 1 electron gets stolen. And the reason is because quantum mechanically it's more stable to have the d block full. That's all you have to tell me in this class. Okay, well, this is not a quantum mechanics class, this is just Intro Chem. So that's all you need to worry about in this class. The same thing would affect silver. The only difference is it would be a 5s instead of a 4s and a 4d instead of a 3d. Okay, quantum mechanically it's more stable to have that d block full. But again, it only affects if you're 1 away. So palladium would have to steal 2 electrons, that's too many. Okay, it's only if you're 1 away. So that's why it's these 4 anomalies. And again, technically it would affect these 4 as well, but that requires you to go through the F block, which you're not going to do. Do we understand these anomalies? These are the 4 anomalies that you're responsible for knowing. So if I said write the electron configuration for copper, and you wrote this, you lose half a point, because this is the actual electron configuration. Okay, that's the actual configuration. If you wrote that, I'd take off half a point, because you need to know that that's the correct. Questions before we stop? Okay, that's where we're going to end for today.